and this is module 8 of the course on econometric modeling. Module 8 presents the assumptions of classical linear regression. So, once we have talked about the basic structure of simple regression, the next thing is the assumptions of classical linear regression. They are very crucial part of any regression analysis, and basically a lot of things, or whether how good a model is, that to a large extent depend on these assumptions of classical linear regression. So, first of all, we define the classical linear regression model. In the specification yt equals alpha plus beta xt plus ut, data for xt is observed, that is they are observations, but since yt also depends on ut, it is necessary to be specific about how UTs are generated. So, most of the assumptions are actually made concerning the UTs, the unobserved error or the disturbance terms. Since XTs are observed, that is why we do not need much assumptions about them, or for the time being no assumptions are made concerning their observable counterparts, the estimated models residuals. Once we obtain the sample from the population, then we obtain the residuals. So, the assumptions are all about the error terms primarily, and they pertain to the error terms. Whether the assumptions are fulfilled, that is certainly checked by considering the residuals or with the residuals, but assumptions are made about the error terms only and not about the residuals. On the other hand, very few assumptions are made about the observed part, that is xt. Most assumptions revolve around the unobserved part. So, the assumptions of OLS are primarily 5. First of all, in the population, the regression model is linear in the parameters. So, linearity, what it implies, why do we need, has already been explained. So, we must have a broad formula or framework of the model as yt equals alpha plus beta xt plus ut, which basically states that the relationship between the variables in terms of the parameters are linear. We have a random sample of size t. So, the sample should be a random sample, where the sample consists of the observations on two variables xt and yt, t running from 1 to capital T. So, here we are considering time series. We can similarly have alternatively t replaced with I. So, we can have a random sample of size capital N, where the observations are on x I and y I, where I equals 1, 2 to capital N. Then we are actually dealing with the cross section data. The sample outcomes on x, namely xt equals t equals 1 to t, are not all the same values. The error u has an expected value of 0 given any value of the explanatory variable. In other words, expected value of u given x is equals to 0. So, so far we have talked about in parts that expected value of u is equal to 0. Now, we are saying that the expected value of u conditional upon the values of x is actually 0. We are going to deal with this assumption, which is a very crucial one, at length in the upcoming slides. The error u has the same variance given any value of the explanatory variable. So, variance of u given x is equals to sigma square. This is also another very important assumption. The error u has the same variance conditional upon the values of x, and this is called the assumption of homoskedasticity. So, in latest slide, when we deal with this assumption, then that would be directly referred to as the assumption of homoskedasticity. So, classical linear regression model, alternatively this yt equals alpha plus beta xt plus ut is known as classical linear regression model or CLRM, given that it fulfills the following assumptions. The first assumption is expected value of ut given is equal to 0, variance of ut is equal to sigma square, covariance between ui uj is equals to 0. So, that is the different observations of the error term are actually independent of each other. If you remember, we had defined in the very beginning that independence between two variables imply that their covariances are 0. Now, a covariance between ui uj is equal to 0 here implies that the observations that the random u or error term has, they are independent of each other. Covariance between ut and xt is equal to 0, that is the regressor is unrelated to the error term. Again, the error term and the independent variables, they are basically independent of each other. And finally, ut follows a normal distribution with 0 mean and sigma square as the variance. So, this actually of course, this is partly referred to by the first two assumption that it has mean 0 and variance sigma square. The only thing that is being added here is that ut is normally distributed. Okay. So, this is an alternative, the same set of observations or assumptions are now written in a different way, and this entire thing together is called or known as the classical linear regression model. Now, the assumption of expected value of u equals 0 is actually not very restrictive as long as the intercept alpha is included in the equation. Nothing is lost by assuming that the average value of u in the population is 0, because even if it is not 0, it can be rendered 0 by modifying the model in such a way that alpha will take care of the non-zero mean of the series, non-zero mean of the error term. As long as assumption 1 holds, assumption 4 can be equivalently written as expected value of xt ut equals 0. So, assumption 1 is expected value of ut equals 0. Now, you can see that assumption 4 said the covariance between ut and xt is equals to 0. So, if you remember, an alternative formula for covariance was expected value of ut xt minus expected value of ut expected value of xt, right. Now, that is why we are saying that the long the first assumption holds that expected value of ut is equals to 0, then this assumption can be written as expected value of ut xt is equals to 0, right. As long as assumption 1 holds, assumption 4 can be equivalently written as expected value of xt ut equals to 0. Both formulations imply that the regressor is orthogonal, that is unrelated to the error term. A slightly stronger alternative to assumption 4 is that xt are non-stochastic or fixed in repeated samples. Okay. So, this actually may also imply that expected value, if xt is fixed in repeated sample, then we can consider xt as non-random, and the moment xt becomes non-random, we can always write expected value of xt ut as xt expected value of ut, or expected value of xt becomes 0, and as a result of which this becomes 0, right. So, but this is a slightly stronger alternative to assumption 4. This is a stronger alternative because we are assuming away the randomness that could be there in xt, right. This means that there is no sampling variation in xt, and that its value is determined outside the model. The fixed in repeated samples scenario is not very realistic in non-experimental contexts. For example, if we collect data on wage and education of individuals, then it makes little sense to think of choosing the values of education ahead of time and then sampling individuals with those particular levels of education. Alternatively, suppose I collect data from 100 individuals and on YT and XT, that is wage and education. Then I go for another set of 100 individuals for collecting data on wage and education. But if I hold XT constant, then this means that I must choose those individuals having the same amount of or same number of years of education, right. So, that education remains constant, only my YT keeps on changing with change in the individuals. So, we are holding the XT or the independent variable constant in repeated samples, which is unrealistic, and as a result of which this is we call a slightly stronger assumption. Random sampling, where individuals are chosen randomly, is representative of how most data sets are obtained for empirical analysis in the social sciences. And if we assume repeated fixed in repeated samples, then this assumption of random sampling is actually lost in the case of or in the context of non-experimental data, right. So, that was a special case, but in general what we have obtained is that the expected value of UT multiplied by XT is actually 0. Alternatively, the covariance between UT and XT is 0, and we have also assumed that expected value of, or one of the assumptions of CLRM is that expected value of UT is equal to 0. Now, if you remember in the previous module while discussing adjusted R square value, I had assumed that 2 multiplied by summation UT into y t hat minus y bar was actually equal to 0, and then I have proved that why that is 0, while I made an assumption that summation UT hat into XT is equal to 0. So, this is actually very similar to this assumption, but this is in the context of population, and if we work with the sample residual, then this assumption, if applicable on the sample residuals as well, then that would mean the same thing, that summation UT hat multiplied by XT is equal to 0, which is alternatively the covariance between the residual and the independent variable is actually 0. Anyway, however, assumption 4 measures only linear dependence between U and X. It is possible for U to be uncorrelated with X while being correlated with functions of X such as x square. So, an alternative and better assumption is expected value of U given X is equal to expected value of U. So, you can see that when we assume that covariance between U and X is actually equals to 0, that is specifically having an expression would imply that expected value of UT multiplied by XT is equals to 0. But the problem is that if UT can be correlated with any other functional form of X, for example, UT can be related to x square, x cube, 1 upon x and so on. So, if we can assume that the errors are actually unrelated to any functional form of x, then we would be writing it as expected value of U given x, that is any value of x, any functional form of x, we are having that equal to expected value of U. So, in particular for any x, we can obtain the expected value of U for that slice of the population described by the value of x. The crucial assumption is that the average value of U does not depend on the value of x. So, U is actually mean independent of x. So, alternatively, expected value of U given x is equals to expected value of U is the conditional distribution of U given any value of x. Here U is said to be mean independent of x. When expected value of U given x is equal to expected value of U and that is equal to 0, we obtain 0 conditional mean assumption. Once we assume that expected value of U given x is equals to 0 and we have random sampling, nothing is lost in derivation by treating the xi's as non-random. So, even if I go for fixed regressor in repeated sample, we do not lose much, because we have already made a stronger assumption that, or sufficiently strong assumption that UTs are actually independent of any value of x. So, you keep x fixed in repeated sample, you keep on changing x in repeated samples, that is no way going to impact the values of UT, or rather the expected values of UT. Given expected value of u given x equals to 0, the population regression function is given by expected value of y given x equals alpha plus beta x, because we have this additional term expected value of u given x equals to 0. This portion is 0, and that is why this is what is our population regression function. Now, we draw this population regression function. So, on the right hand side you can see a diagram where for various values of x1, x2, x3 we have certain values of y. Now, you can see that if in repeated samples, if I collect samples repeatedly and x values are fixed, then I can have for fixed value of x1. So, we have taken 3 alternative values of x, x1, x2, x3, and for individual value of x we have different observations of y, right. And this is my fitted line, which is the population, this is actually the population regression function. In the population, this line would fit the data given as alpha plus beta x. So, this is the line which is passing through, and these are the points of yt hat. So, this is y1 hat, which is actually given as alpha hat plus beta hat x1. Similarly, this is my y2 hat, where this is equals to alpha hat plus beta hat x2, and I can also have y3 hat, and all of them together construct my yt hat series, right. Now, this tells us how the average or expected value of y changes with x, or a 1 unit increase in x changes the expected value of y by the amount beta. Also, this implies that for any given value of x, the distribution of y is centered about expected value of y given x. So, this is the distribution of y for any given value of x, they are centered around the distribution of y. The population regression function is centered is at the center, and the distribution of y is centered around or about the population regression function. So, its counterpart for the sample is sample regression function, or SRF. Population regression function is fixed but unknown in the population, and that is why the SRF is estimated PRF. So, with sample we try to estimate the population regression function, and that is denoted by the sample regression function, which is yt hat equals alpha hat plus beta hat x. Now, because the SRF is obtained for a given sample of data, our new sample will generate a different slope and intercept, right. Every time we change the sample, our alpha hat and beta hat values are expected to change. How good a set of estimates are, whether one can have confidence in the estimates, and whether they are likely to vary much from one sample to another sample within the given population, is given by the standard errors of the estimates. So, we have a set of estimates given by different samples. So, as samples changed, my alpha hat and beta hat values changed. That is how if I draw 100 samples, I will be getting 100 estimates of alpha hat and beta hat, and these 100 estimates are never going to be the same because my sample has changed, or whatever be the variations among them or between them, that is measured by the sample variance or variance of the sample estimates or their standard errors. So, variance square root of variance is generally standard deviation, but when it comes to the estimators, then square root of variance is known as standard error. So, they provide us an idea of the sampling variability, how much my sample is actually or how much my parameter estimates are varying due to variations in sample. So, next we talk about the last assumption of homoskedasticity. I mentioned that homoskedasticity implies constant variance of the error term. Homoskedasticity or constant variance assumption states that the error u has the same variance given any value of the explanatory variable. In other words, variance of u given x is equal to sigma square. You can see that sigma square is a constant number, it does not have any subscripts like t, I or no variable is associated with it. So, it is a constant number, and as a result of which this refers to the assumption of homoskedasticity, which implies that the error has constant variance. The importance of this assumption will be reflected in deriving the properties of OLS estimators and their variances. Since variance of u given x is equals to expected value of u square given x minus expected value of u given x whole square, and expected value of u given x is equals to 0, as you can see, then expected value of u given u square given x is equal to sigma square. Sigma square is also the unconditional variance of u. So, variance of u is equal to sigma square, which implies that here we are deriving the variance of u conditional upon the values of x, and we are getting sigma square. So, this is the conditional variance of u given x, and this is the unconditional variance of u given x, both are sigma square. Sigma square is often called the error variance, and sigma is the standard deviation of the error term. Now, the simple regression model under homoskedasticity, how does it look like? So, in the previous graph I had shown you how the population regression function looks like. That was a 2D graph where we are measuring y on the vertical axis and x on the horizontal axis. Now, if you also turn this diagram, just ignore this part and look at this part, then it would look very similar to what was shown in the 2D diagram. Now, by considering a 3-dimensional, where on the third dimension we are measuring the functional form of y given x, right. So, this actually talks about the importance of homoskedasticity. You can see that for given values of x, the values of y are, these are the values of y, they are centered on the population regression function, but their variations around the fitted line or the population regression function is constant. So, the variations here, the variations here, the variations here, all are same, all do look very same, and this is the assumptions or implication of homoskedasticity, as opposed to the assumption of heteroskedasticity. I will also show you a graph quickly, which shows how heteroskedastic errors would look like. Now, given the assumption of homoskedasticity, variance of y given x is equals to variance of u given x equals to sigma square, because for given values of x, alpha, beta and x all are constant. So, my original y is alpha plus beta x plus u, right. When I am considering variance of y, and that is conditional upon x. So, which implies that for given values of x, I am trying to find out the variance of y. In that case, my variance of alpha plus beta x would be actually 0, because they are now no more random variables, they are not varying altogether, their variations would be 0. So, their variance is 0. So, what I am left with is actually variance of u given x, and then there will be covariance terms between u and this part, that is alpha plus beta x. So, by now we know that the covariance between u and x is 0. So, anyway this part also becomes 0. So, that is why variance of y x is equal to variance of u given x. When variance of u given x depends on x, the error term is said to exhibit heteroskedasticity or non-constant variance. Because variance of u given x is equals to variance of y given x, heteroskedasticity is present whenever variance of y given x is a function of x. So, this is the presence of heteroskedasticity graphically. You can see that for individual values of x, these are the values of y in repeated samples, and you can see that the variations are not same for different values of x's. So, when we are changing x, then the variations in y is actually not constant. So, variance of y given x is not constant, right, and this is the problem of heteroskedasticity. Somewhere the variations are different, that is reflected through these graphs, that is how they are distributed. The distributions are changing, some are nearer to the mean, some are actually much broad tailed or fat tailed, as a result of which the variations are changing continuously, and we do not call it a homoskedastic error terms or homoskedastic y series, they are heteroskedastic. So, that brings me to the end of this module. We will continue with the properties of OLS in the next module. Thank you.